Hey everyone, welcome back to Linear Algebra. This will be part B of lecture 16. And so where we left off, we had just defined, in the first half of the lecture, we defined linear independence and conversely linear dependence. And we had some very nice theorems for identifying when a set S in a vector space V is a linearly independent set and when it's a linearly dependent set. Right? So our definition of, so a lot of the theorems that we had previously talked about dealt with vectors, subsets S of a vector space V that were non-empty and finite. But what happens when your subset S of a vector space V is an infinite set? Right? So what can you say about the linear independence or dependence of an infinite set? Right? So what about when S in V is infinite? Right? What happens when your subset S has an infinite number of vectors in it, which obviously can happen. We could rattle off a ton of examples of that right now. Let's talk about the theorem. It's actually very, very nice theorem. You may think this is going to be a really nightmare, but it actually is a very simple addition to some of the previous theorems. So let's let S be a non-empty subset of a vector space V. Okay, then S is linearly independent It's linearly independent if and only if for every finite subset V1 ... Vn, so every finite subset of vectors in S, the equation A1 V1 plus A2 V2 plus ... plus AN Vn equals 0 implies that A1 equals A2 equals ... AN equals 0. This is almost exactly the same as the previous definition, except here, we're allowing for the case of an infinite subset S of a vector space V. Right? The only thing we have to check is that, hey, in general, if I grab a subset out of S and I set up this equation with that subset of vectors, does that imply that all of the coefficients, all the scalars are 0? If it does, which is the exact same condition that we needed before in the case of a finite subset, if it's true for every finite subset of an infinite subset, then the infinite subset is linearly independent as well. Okay, so it's the exact same condition, basically. Okay. And so let's see an example of how this plays out. Let's let S equal the set x cubed, x to the 5th, x to the 7th, ... right? All of them, all of the polynomials with odd degree. Okay, let's let S equal that. This is obviously a subset of P of all polynomials, but S is infinite, isn't it? Right? I mean, this is obviously an infinite set. Okay, so the question is S linearly independent? Is S linearly independent? Right? Are there any vectors that'll be in S that can be written as linear combinations of the other vectors in S? Okay. Well, this is a linearly independent subset of this larger set P, right? And it's because the S contains the powers of x that are odd, and specifically beyond that, all of the powers of x have distinct exponents, right? So if all of the powers of S, of the elements of S, if all of these exponents are distinct, then any finite linear combination of these powers can produce the zero polynomial only if the coefficients are all zero. Okay, so let's see an example here, right? Let's consider, let's grab a subset of S. So let's say S1, right? Doesn't matter how you label it. Let's consider a subset of S, and let's call it S1. So it'll just be x cubed, and x to the fifth, right? This is obviously a subset of S, which is itself a subset of P. Okay, and so let's consider the generic form of the vectors in S, right? So, well, of the linear combinations of S, right? So you'd have like a1x plus a2x cubed plus a3x to the fifth, right? And if I set that equal to 0, right, what possible values of A could I have here? Right? What possible values of A1, A2, and A3 are even allowed here, would even work? Well, this is only going to be true if A1, A2, and A3 are all equal to 0. Okay, that's the only time this is going to happen, right? Right, so this is a perfect example of an infinite subset. It doesn't matter, which it doesn't matter which particular terms I grab out of S. I could grab x to the 100th power, x to the 5,001 power, x to the 1,000,003 power. Right? So long as they're all odd and they're all actually in S, this equation is always going to imply that A1, A2, A3 equals 0. Okay. Perfect. Okay. All right. All right. So let's go ahead and move on to what is probably the most important theorem of this section. And it's very important not only because it's a big theorem, but it's an important theorem because it's going to be sort of the basis of what's to come. Okay, so this theorem will pretty much serve as the foundation for much of the rest of our vector space discussions, right? And so here it is. Let's just write it out, and then we'll talk it through, and we'll write a proof of it. So let's let S be a non-empty subset of a vector space V. Okay, we'll let S be a non-empty subset of a vector space V. Okay, then S is linearly independent. Right? It's linearly independent if and only if every vector V in the span of S, okay, every vector V in the span of S can be expressed uniquely key thing here being uniquely, can be expressed uniquely as a finite linear combination of the elements of S. Okay, and when we say uniquely, we mean uniquely ignoring terms with 0 coefficients. okay, with coefficients equal to 0. All right. Okay, so what is this saying? This says, S is a linearly independent set if and only if every vector in the span of S has a unique linear combination, right, of the elements of S, right? So if S is linearly independent, then anything in the span of S can be written as a linear combination of the elements of S, and not just that, can be uniquely written, right? So it means there's only one linear combination for each of the vectors in the span. Okay, and this is ignoring terms with coefficients equal to 0, right? Because obviously I could leave in or omit terms with 0 coefficients, meaning I could create redundant or distinct ways of writing it. But if you ignore the terms with 0 coefficients, all the non-zero terms, they produce a unique linear combination of the elements in the span. Okay, so that's kind of different. I mean, you may not have seen that coming, actually. And I know the first time I encountered that theorem, I thought, oh, geez, that's a little bit surprising. That was a little bit surprising to me. So let's actually prove this. I think we can do this. It shouldn't be too bad. It's a little bit of an involved proof. It's not too bad, though. It might be kind of at the edge of what we're comfortable doing in linear algebra. But let's go ahead and try it. Let's try to write it out. And we might cut some corners here and there, but this should give you a good sense for why this works. So let's this is an if and only if. So let's start by going one direction, and in this direction we'll say we're going to assume S is linearly independent. We'll assume S is linearly independent and that V is in the span of S. Okay, and what we're going to do is we're going to assume the reverse. Okay, and we're going to assume that V can be written using two distinct linear combinations. Okay, so assume S is linearly independent and V is in the span of S, and that V is equal to A1 U1 plus dot 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 plus A, and we'll say this is K UK. Okay, and these U1 through UK are obviously vectors in S. So V can be written in this way, and V can also be written in this way, B1 V1 plus dot 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 plus B L VL, we'll say. Okay, so these two different ways of writing V are, they're different, they're distinct. Okay, right? So again, kind of keep your assumptions in front of you. So S is linearly independent and V is in the span of S, and V has these two unique linear combinations. Right, we'll just call them combination 1 and combination 2. Right, unique. Right, specifically we would say that 1 is not equal to 2 in the sense that at least one of the terms vary. And we'll say at least one of the non-zero terms vary. Okay? All right, so maybe A1 U1 and B1 V1 are distinct terms, but everything else is the same. That's possible. Right, so let's go ahead and just throw that out there. We're giving it the most possible, the largest possible breadth, as we can say. They're just different in some sense. Okay. So think of that, and so since some of these UIs are going to be different than some of these VIs, right? So these UIs and the VIs are all vectors in S. Some of them are different, though. Some of them may not be used over here, and some may be used over here, but some of them would be the same also, potentially, right? So some of the UIs may be the same as some of the VIs. Right, so we need to kind of account for this some way, we need to come up with some way of accounting for the fact that some of these vectors are the same. So what we're going to do is we're going to use a trick that we've used a couple lectures back, where we create this new set X, which is the union of all the vectors used in these two combinations. So this would be the union of U1 dot 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 UK, and also the V1 through VL. Right, remember these are vectors, right? And so this is going to be some subset also of S, right? So X is a subset of S. Okay, so we're going to let X equal this union. And what we're going to do is, so inside this union, some of these will be the same, right? So as I said, maybe it's possible that U1 and V1 turn out to be the same vector, and maybe U5 and V11 are actually the same vector. Whatever that happens to be, we are going to relabel the distinct vectors as a different set. So label the distinct vectors from X as W1 dot 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 WM, right? Not all of these indices are, don't worry about what's, L's less than M, M's less, they're all different, right? So however, many are, there are no more W's than there are U's and V's, right? So some of these are going to be dupes. We just threw out the dupes. So all of these are different now. So all the W's are taken out of X, and they're all distinct. We just got rid of the duplicates. Okay? All right. Right, so we got rid of all the duplicates from U1 through UK and V1 through VL, and we've just relabeled them as W1 through WM. So that being the case, we can revisit these linear combinations here and re-express them in terms of W1 through WM. Right, so let's re-express 1. Right, so 1, we said initially that it was equal to A1 U1 plus dot 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 plus AK UK. Well, we don't know what all of those are, but we know that U1 through UK, all the distinct vectors there are captured in here, so let's rewrite them in terms of W1 through WM. So that means V is equal to C1 W1 plus dot 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 plus CM WM. Right, now some of these C's may be 0 if the vectors, if WM, for example, isn't one of these vectors. It might be, you can just write it as 0, that's fine. But we're going to express V using all the vectors. And the ones that aren't relevant, just put a 0 in front of them, no problem. And we'll do the same thing for the second linear combination here. Remember, these two are distinct. So V is equal to B1 V1 plus dot 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 plus BL VL. Right, and we're going to rewrite that one in terms of W's as well. Right, so again, some of these W's may not be relevant, so we'll just put a 0 in front of the ones that aren't relevant. But this V1 is one of these vectors, so put it in here. The V2 down here was going to be in here, so grab that one, and so on. Right, and so we can write V is equal to D1 W1 plus dot 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 plus DM WM. Okay. Now you may be saying to yourself, how is it that these vectors can be rewritten as linear combinations of the same count of vectors down here, but here we had K and L? Well, again, remember, some of these coefficients will be 0, and some of these will be 0. Right? The whole point is just to line them up on the same set of vectors. Some of them will be 0, some of them will not be 0. Right? And so if there were fewer vectors in this one than there were in this one, then there'll be more zeros when we rewrite this here. Okay, that's all there is to that. There's nothing tricky there. Okay. All right. So the fact that these two linear combinations are different, right, by assumption, implies that at least some CI/DI is different here. Okay. Right, some CI/DI is different. Maybe all of them are the same except for one. That's possible, right? But somewhere there's a difference. Okay. Okay, and let's see what that gives us then. So I've got these two linear combinations. They all have the same number of terms. So let's do some subtract one from the other. right? So I'll take v minus v. Okay, right? So if I subtract those two, I know those are the same vector over here. That's equal to the 0 vector, right? And if I just subtract these component-wise, I'll get c1 minus d1, w1 plus c2 minus d2, w2 plus dot dot dot, plus cm minus dm, wm, right? Okay. Now, what do we know about w1 through wm? Well, they come from S, right? Right? They come from S. S is what? S is linearly independent. Right? S is linearly independent. So W1 dot 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 Wm, this is a subset of S, which is linearly independent. What does it mean when you have a linearly independent set S and you have a finite subset of that linearly independent set? What does that imply for this homogeneous expression? Well, it means that all these coefficients have to equal 0. Okay, so if this is from S, which is linearly independent, that implies that Ci minus Di equals 0 for all I. Right? Now, what's wrong with that? Well, the problem is we assume that one of them's different. Right? So this implies a contradiction because we assumed that some Ci was not equal to Di. Right? We assumed this up here. Right? So, right, remember, 1 is not equal to 2 in the sense that at least one of the non-zero terms vary. Right? Well, now we've aligned all the vectors, so the only way that they cannot vary is in the coefficients, or the scalars up front. Right? So we have a contradiction. And so what does that mean for us? Well, it means that if S is linearly independent, and V is in the span of S, then V has to have a unique linear combination that expresses it. You can't have these distinct linear combinations. Only one works. Okay. Kind of a tricky proof. Kind of goes around and around a little bit. Take your time. This is just, a quick outline of it. Take your time, really rough it out in detail. Let's go the other direction, though. And that was just one direction. The other direction's quite a bit simpler. So here what we want to do is we want to assume that every vector in the span of S can be uniquely expressed as a linear combination of the elements of S. Okay, all right, so let's assume that every vector in the span can be uniquely expressed as a linear combination of S. Well, then 0 is in the span of S. We know that, right? Okay, so 0 is in the span of S. And so there exists exactly one linear combination of elements of S that equals 0. So there exists exactly one, right? Exactly one linear combination of elements of S that equals 0. That kind of gets you there, doesn't it? Can you see where it's going to go next? Right? So if, what happens? Well, if you have, let's write them out, V1 through Vn, it's a subset of S. If you have some finite subset of S, the fact that the 0 vector, which is in the span of S, must be equal to 0 V1 plus dot 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 plus 0 Vn means that the only possible coefficients are all 0, right? And so that implies that S is linearly independent, right? So this is one way to write it, and in fact it must be the unique way to write it, right? And so this is going to imply that A1 is equal to A2, which is equal to dot dot dot, AN, which is equal to 0, right? And this was the condition, right? This equation implying this fact about the scalars was the condition needed for linear independence. Okay. And that's what we're trying to prove, right? We're saying if every vector in the span can be uniquely expressed as a linear combination of S, then that implies that S is linearly independent. Okay, and that's the proof. Excellent. Okay, and again, you could fill in some of the gaps here. We're just kind of ripping through it, getting the rough outline of it. Okay, perfect. So that covers what we need to talk through for linear independence. And the next lecture, we'll get into basis and dimension, right? So we're midway through our vector space series. So this will be the 4th lecture of the vector space series. We've got 3 more after this, and we'll talk about basis and dimension next, and then we'll get into how to construct special bases and coordinatization of vectors. So, all right, take care, and we will talk to you all next time.